Section 7.4 is arc length. It's another integral application. And we see on this page that we have a direct arc length formula as an integral here. And that's for a function y equals f of x, which has a derivative f prime that's continuous on this interval a to b. And we're, of course, looking to find the arc length of that function over the interval a to b. So where does this thing come from? It looks like a fairly esoteric formula. So let's have a look at a graph or a picture that might show us how this thing comes about. So imagine we're given a function y equals f of x. That's this arbitrary curve drawn here. And we want to find its arc length from, say, a equals 1 to b equals 6. So one can imagine that a way to approximate that is to split up this interval into these line segments. In other words, approximate the curve with these line segments. Now, the smaller we make the line segments, the closer we are to having the actual length of the curve. And that'll be the job of the limit ultimately in this process. But let's look at this sort of fixed frame here. We have L1 through Li. These are the lengths of each of these line segments connecting these points along the curve. And if we wanted to find the length of Li, the ith line segment here, generally, then we consider the fact that there's a right triangle formed by the change in x and the change in y along this curve. So in other words, as we move from this point to this point, we have some delta x. In other words, some distance that we move along the x-axis. We have some distance that we move along the y-axis. And that, of course, x and y components are 90 degrees from each other. So we have a right triangle, and the hypotenuse of that right triangle is L sub I. So that means that Li squared is equal to xi squared plus delta y squared. So if we take the square root of both sides, we just get that Li is equal to this radical expression on the right. So that's for one line segment. We could add that up for all of these. If there were n of them total, then we'd have the sum of n of these Li line segments. And we start to see how this comes together. We can substitute for Li, this radical expression that we saw geometrically up above. So we end up with this sum, summing up all these square roots. And then let's factor out delta xi squared. So when we do that, it divides out of this term, and we end up with delta yi squared over delta xi squared. And when we factor delta xi squared away from these two terms, and it's underneath the radical, it just becomes delta xi. So in other words, if we were to pass this back in and multiply by both those terms, it would have to be delta xi squared, since that's what it is underneath the radical. So with this in hand, we can see that we have most of the formula here in front of us, actually. So if we take the limit of this Riemann sum as n goes to infinity, well, if we form the Riemann sum by taking the limit as n goes to infinity, to speak precisely, then we have the integral from a to b of this delta xi becomes dx. And that's, of course, assuming we take uniform interval lengths and things like that. There's a little bit of mathematical detail that we're not taking care of right here. But this delta yi over delta xi becomes dy over dx. It's a common thing we see in these calculus classes or operations where we have a delta y, delta x. We take the limit as n goes to infinity. And then that delta becomes a d, becomes this infinitesimal differential dy or dx, or whatever might be suitable. So that's our formula. It comes about thanks to this situation, this Pythagorean theorem up above in those line segments, approximating the arc length of this curve. You take the limit, that gives you the integral, and we have the exact arc length from a to b for a curve y equals f of x. Now, it's nice and easy. It's a formula we can use. The hard part is we have a radical and an integral to start with. So this isn't necessarily going to be a very easy integral to evaluate. So let's have a look at some examples. The first one is to find the arc length of the given curve along the interval 0 to 1. So the curve is y equals square root of 4 minus x squared. Our arc length formula is this. They give us everything we need. We have the function, f of x, we have a, we have b, as 0 and 1, and we set up our integral. We need to take the derivative of f of x first. And we have ultimately here that is negative x times 4 minus x squared to the negative 1/2. Note there was a chain rule. That's how that came about. I'll let the reader take care of those details. And then lastly, we know we're going to square that derivative, so we might as well square it over here before we plug it all in. And when we square this term, we get the highlighted portion below. So that's f of x squared right here plugged into our function. Well, it doesn't look good right now, but the best thing we can do is maybe rewrite this negative exponent so that it represents the fraction or the rational expression that's involved. Then, next step, just consider a common denominator. You're not going to simplify two terms under a radical, but you might be able to simplify a single term, right? In other words, if we can get rid of this plus sign, maybe we can simplify things. So a common denominator, turning 1 into 4 minus x squared over itself. We end up with combining those numerators, we get 4 over 4 minus x squared. That's 2 over root 4 minus x squared. This is looking quite a bit better. And by the time we arrive at this position, we see that we have nothing more than a trigonometric substitution integral. That's off to the side here in case the reader needs the details, but by now you should be proficient with those. So you carry out the trigonometric substitution. Looks like we end up in a variable theta, and we come back into a variable x, and we ultimately evaluate at our endpoints, and we get pi over 3. Okay, so take your time, pause the video there if you need to work out those details, but otherwise, we've done the arc length portion of this problem. So next, find the arc length of the given curve along the interval 1 to 9. So we have x is equal to 1/3 root y times y minus 3. So x is now a function of y. I've written g of y just to keep that in mind. And just to sort of adapt our formula. Our formula is in terms of x and f of x, but it could also be done in terms of g of y and dy. And that's exactly what this is right here. So now we just think about moving along the y-axis. Or if we're given everything in terms of a y variable, we just do this all in terms of a function of y and the differential y. So this is g of y. When we simplify it a little further, we get the following. That's writing square root of y as y to the 1/2, and then distributing that product, that multiple across y and minus 3. We end up with this expression here, of course. Now, the derivative of that is just a straight power rule on both of those terms. Then we're going to square it. So we're squaring this expression. And once we get done with that, we have this expression. Okay, we could just go run and plug this right back in, and we probably would. We didn't know otherwise. So I could plug that in right here. But let's slow this down for a moment, and let's have a look at something. This g prime of y function squared, we're going to add 1 to it thanks to the formula under the radical here. So let's see if we can simplify that before we plug it in. You don't have to do this analysis here. You might plug it back in and then realize, okay, I need to do some more work off to the side in terms of algebra. So you could just come right back down to here and start from this step after you've plugged it in. But what you should notice is when you add 1 to this highlighted expression here, the 1 and the negative 1/2 combine, and you get positive 1/2. Okay, this is a perfect square trinomial right here. We know that because it came from squaring this binomial. Okay, so when we add 1 to this and we get positive 1/2, we should suspect that this is also a perfect square trinomial because the only difference between its middle terms, its middle term and the other one's middle term, is the plus or minus sign. And that in fact is the case. It turns out that this one is a perfect square binomial, only instead of a minus sign in between, we have a plus sign in between. Okay, another way to see this, if it's really difficult to deal with the y to the negative 1 power that I haven't really talked much about, you could think about it this way. You could write down 1 plus g of y down below. I'll add one more line down here in red. 1 plus g prime of y squared. To rewrite that, we have 1/4 And we can write y squared. I'm just going to multiply everything by y, 1/2 y plus 1/4. And then what I'll have to remember is that I multiplied everything by y to the first power. So I need to offset for that and decrease y to the -1. Okay, so that's essentially the same thing that we have here, right? If you multiply through by y to the -1, you'll recover that expression. Okay, now what this does though is it allows us to see that, oh yeah, this is a quadratic and it will factor as we expect. So you'd get 1/2 y plus 1/2 quantity squared. Y to the -1 would be outside of that. To pass that in, it comes in as y to the -1/2, and that would change all those factors. I don't think that's the easier way, but some students might see that a little bit better than what I have here. Takes a little bit of practice, but this is that disguised quadratic scenario that I've warned about before. Okay, so once we have that, the reason we want to be able to factor this into something that is a quantity squared is, of course, because we have a square root around that. So if we can rewrite this as a full quantity squared, then we can just cancel this square root with this square. So this square on the outside of all this cancels with this square root. Note that that's not the case. This still happens. You cannot cancel this square root with this square because of this +1 right here. Okay, the square root of a plus b is not the square root of a plus the square root of b. That never works. Try that for a equal to 1 and b equal to 3 and see what you get on either side of that. So in other words, what I'm saying is the square root of 3 plus the square root of 1 equal to the square root of 4? Absolutely not, right? Square root of 3 is irrational, plus square root of 1 is 1, is equal to root 4 is 2. No, those things are not equal at all. You cannot split square roots over sums, so don't try to simplify that way. Now, the square root cancels, and we end up with just what's underneath the radical, just the radicand, and now we have, at this point, a power rule integral, evaluate at the limits of integration, and we arrive at our answer below. So it takes some time to work out the details of that. The hardest part of this one, of course, was seeing to factor this back into a binomial, okay, realizing that it is a perfect square trinomial. It won't be the only time that trick shows up in these problems in this section. Okay, the next problem is to find the arc length of the parabola y equals x squared from 0, 0 to 1, 1. So y equals x squared, or f of x equals x squared. The derivative is 2x. 1 plus 4x squared is our 1 plus f prime of x squared term. We can pack all of that into the radical for our general formula. We're going from x equals 0 to x equals 1. So we integrate from 0 to 1. And we have 1 plus 4x squared underneath that radical. And we can factor out 4 away from each of these to get this into more of a standard form. In other words, an a squared plus x squared form. And then the longer work begins, but at this point, it is just essentially a trig substitution problem. And so since we have an a squared plus x squared problem, we use a squared is 1/4, a is 1/2, so x is 1/2 tangent theta. All the things that ensue from this substitution come about now, and then we work this integral all the way through. You see there are quite a few details to it. I don't think it's necessary that we work all of these out. We end up in a variable theta for a while. We make a note that x is, our limits of integration are in terms of x. So when we're done working in terms of our variable theta, we need to get back to a function of x, or simply change our limits of integration. It's one way or the other. In this case, I found it easier to just change back to x and evaluate at those limits of integration, and we come out with our result. So much of this is not anything new. It's just an application of this formula, and then it's chapter 6 type integration to follow. Okay, so the good news is it's also some practice for chapter 6. Okay, another upshot to that, another upside to that. So a final example is an application And we have a wire that's suspended between two telephone poles with the midpoint of the poles on the ground at the origin. So the midpoint between these two poles represents the origin on the ground, at least, right here at the level ground. Each pole is at x equals negative b and x equals b. So for each of these two poles. And then we're given that the equation that describes the curve the wire forms is y equals c plus a hyperbolic cosine of x over a, and that's called a catenary. They ask us to find the length of the wire. Okay, so it's an interesting fact that when a wire hangs suspended or any kind of loose pliable material hangs between 2 points like this, it forms a catenary. So that exact curve is given as we have it here. Okay, so they're asking us to find the arc length of it. So we're going to go from negative b to b as our interval, and then 1 plus f prime of x squared. So we need to find the derivative of this function with respect to x, then we'll square it. We've got a couple nice facts up above. The derivative of hyperbolic sine of x is hyperbolic cosine of x. The derivative of hyperbolic cosine of x is hyperbolic sine of x. Okay, this is the type of derivatives that you wished that sine and cosine had, because you notice there's no plus or minus sign that comes about in these, right? So we just have very straightforward derivation for these two functions. By the way, the definition of these two functions, hyperbolic sine of x is e to the x minus e to the negative x over 2, and hyperbolic cosine of x is e to the x plus e to the negative x over 2. So once you see that these functions are defined by the exponential or a function of the exponential function, you can realize that maybe that's why the derivatives turn out so nicely, right? It's very interesting that sine and cosine and the exponential function have this relationship through these hyperbolic sine and cosine. Okay, so that's all we need to know about this. That section often gets skipped in a Calc 1 class, but we know the derivatives of hyperbolic sine and cosine. That's completely sufficient for now, because what we do next is we find the derivative of this function with respect to x, and that's given below. We have f prime of x, and of course c is just a constant, so when we take its derivative with respect to x, it's 0. And we have a hyperbolic sine from the hyperbolic cosine. And then that's times 1 over a. That's a chain rule from this term. Taking the derivative of x over a, we end up with 1 over a. So the a and the 1 over a cancel to 1 in their product. And we just have the hyperbolic sine of x over a. So now we plug that into our function, or into our radical within our integral. So 1 plus hyperbolic sine squared of x over a dx. And then again, well, there was one more thing we needed to know. 1 plus hyperbolic sine of something is hyperbolic cosine squared. So 1 plus hyperbolic sine squared is hyperbolic cosine squared. And then whatever those arguments are, need to match. Okay, that can be derived somewhere also. We've got it written off to the side, more or less as written. Well, that looks like it's off by something. We'll write it as follows. 1 plus hyperbolic sine squared of x is equal to hyperbolic cosine squared of x. That's the identity we're actually looking for. This one's not correct. So once we're able to swap that out, we have a single term squared underneath this radical. This is always the crux of the arc length integral problems, is getting rid of that radical or working your way through that radical. In a lot of cases, it's an algebraic trick like this to do some substitutions and compact terms into multiple terms into a single term and get that square to cancel with the square root. It's exactly what's happened here. And we take the antiderivative of hyperbolic cosine of x over a. Well, that's going to be hyperbolic sine. And then, well, u substitution could have handled this portion, but we end up with this multiple a. Maybe if you're not sure why that a shows up, either take the derivative of this expression to see that it's true. That's a nice way to check something like this. Or do the actual u substitution back here saying that u is equal to x over a, and then work out the details to get to the next step. At any rate, we evaluate from negative b to b, and we've got sine of b, hyperbolic sine of b over a minus hyperbolic sine of negative b over a. And it turns out that the hyperbolic sine, interestingly enough, is an odd function. So it passes this minus sign out of its argument and in front of itself. So that the minus sign in its argument cancels with the minus sign in front of it. It becomes positive hyperbolic sine of b over a. So then we have positive hyperbolic sine b over a plus the same. So we have 2 hyperbolic sine of b over a. And then we have that factor of a. So then overall, this is 2a hyperbolic sine of b over a. So that may have been a little bit of a crash course in hyperbolic trigonometric functions. We just saw their definition, we saw one of their identities, and we've seen their derivatives now. If the reader wants to know a little bit more about these things, which is useful because we'll see a couple more problems with these hyperbolic functions, take the derivative, prove this derivative formula with this definition that we have here. So in other words, take the derivative of hyperbolic sine of x by taking the derivative of this function, and what you should see is that you actually get this function, which is hyperbolic cosine. And that's your path to connect this to this. You could do the same for the derivative of hyperbolic cosine to get to hyperbolic sine. And you could also, a little bit more advanced, prove this identity below. 1 plus hyperbolic sine of x squared is equal to hyperbolic cosine of x squared. So anyway, that's it for 7.4. Again, the trick is handling or negotiating your way around or through the radical in these integrals. In cases where that's not possible, we just end up using approximation techniques like Simpson's rule or the midpoint rule. But most of the problems we'll see will be integrable or tractable in terms of an analytic function. So that should work out.